Welcome to today's Explainer. Get ready because we are stepping into an abstract yet completely fascinating microscopic world to explore the hidden secrets of chemical equilibrium. The principles we're going to look at today, well, they govern this unseen, perfectly balanced chaos that's happening literally inside and all around us every single second.
Okay, so I want you to picture an ordinary, unopened, sealed bottle of soda just sitting right there on a table. At the macro level, looking at it with our own eyes, it appears completely static, right? There are no bubbles rushing to the surface, absolutely no movement. It kind of just seems like a completely inactive, dead system. But we are going to challenge that assumption right now. What if I told you that beneath that calm, boring surface, there's actually a frantic, nonstop flurry of activity?
And that brings us to the core concept of this entire explainer, the illusion of stillness. What looks like a dead stop to our eyes is actually a chaotic two-way street down at the molecular level. Molecules are constantly escaping from the liquid up into the gas phase, while simultaneously, and here's the kicker, an equal number of gas molecules are diving right back down into the liquid. It's this furious, invisible exchange happening right before our eyes, but it's so perfectly balanced that we don't actually observe any overall change. It's wild.
So here's our roadmap for today. First, we'll unpack the illusion of stillness. Then we'll move right into the dynamic nature of equilibrium. After that, we'll tackle the equilibrium constant. And finally, we'll wrap up by looking at gases, pressures, and phases.
Section 1. The illusion of stillness. Physical processes.
Let's formally define what we're talking about here, dynamic equilibrium. This is the state where the rates of the forward and reverse processes become exactly equal, which results in zero observable change. Let's think back to our closed container of water. Water molecules that have higher kinetic energy are evaporating into vapor, right? While at the exact same time, vapor molecules are striking the surface and condensing back into liquid. When that rate of evaporation precisely equals the rate of condensation, boom, the system has reached a dynamic equilibrium. So it's incredibly stable, yes, but it is absolutely not static.
Section 2. Dynamic nature of chemical equilibrium.
Okay, let's dive into this and try to visualize this invisible process. I want you to imagine two measuring cylinders. You fill one halfway up with colored water, and you just leave the other one totally empty. Now, take two glass tubes that have the exact same diameter. You dip one tube into the first cylinder, cap it with your finger to trap the water inside, and transfer it over to the second empty cylinder. But at the exact same time, you use the other tube to transfer water from the second cylinder back into the first. Keep doing this simultaneously, over and over. Eventually, you'll notice the water levels in both cylinders stop changing. They become completely constant. But wait, are you still scooping water? Yes, you are. The levels are constant not because you stopped working, but because your transfer rate forward exactly matches the transfer rate backward. It is such a perfect, totally relatable analogy for how reactants and products transfer back and forth on that molecular two-way street.
And this brilliantly illustrates a really common misconception. We often falsely expect that chemical reactions just hit a dead stop when they finish, like they cross a finish line and just sit down. But in reality, it's a completely different story. Chemists actually proved this dynamic nature using something called the Haber process, which is how we synthesize ammonia from nitrogen and hydrogen. So they let the reaction reach equilibrium, right? And then they introduced deuterium, which is just a heavy isotope of hydrogen. Now, if the reaction had truly just stopped, that deuterium would literally just sit there doing nothing. But instead, the atoms continuously scrambled. They suddenly started finding ammonia molecules that actually contained the deuterium, completely proving that the forward and reverse reactions were still firing away, constantly swapping atoms around without changing the overall net composition. How cool is that?
Section 3. The equilibrium constant. Measuring the balance.
Now you might be wondering, how do we actually measure this invisible balancing act? Well, in 1864, Norwegian chemists Goldberg and Wage proposed the law of chemical equilibrium. And don't worry, it's not some daunting algebra. It's essentially a very straightforward products over reactants story. So Kc, right here, that is our equilibrium constant. It simply equals the concentration of the products divided by the concentration of the reactants, with each one raised to the power of their stoichiometric coefficients from the balanced chemical equation. Basically, it's just a super precise ratio that tells us exactly where that moving two-way street naturally likes to settle.
What's really interesting here is just how beautifully flexible this mathematical rule actually is. Because Kc is a fixed ratio at any given temperature, if we modify the way we write the chemical equation, the constant expression shifts in a totally logical way. So, if you write the reaction in reverse, literally just swapping the products and the reactants, the new constant is simply the inverse, just 1 over Kc. And if you multiply the entire chemical equation by a factor of n, well, the new equilibrium constant is just the original Kc raised to the power of n. It's elegant, and it really proves just how deeply interconnected the math and the actual physical reality of the reaction really are.
Section 4. Gases and Phases. Real-world Applications.
Okay, let's bring all this abstract math right back to the real world. Let's revisit our sealed bottle of soda from the very beginning of the explainer. We know it's sitting there in a state of dynamic equilibrium. But what happens when you actually open it? Seriously, why does soda go flat?
Well, this is Henry's law in action. Consider how soda is bottled in the factory. It is bottled under incredibly high pressure, which basically forces a massive amount of carbon dioxide gas to dissolve straight into the liquid. Once sealed, it reaches that dynamic equilibrium we've been talking about. But the very second you twist open that cap, whoosh, you suddenly drastically drop the partial pressure of the CO2 above the liquid so it matches the regular atmosphere in your room. And because the concentration of dissolved gas is directly proportional to the pressure above it, the whole system is suddenly no longer balanced. So what happens? The dissolved CO2 rapidly escapes the liquid as bubbles, trying to reach a brand new equilibrium condition that matches that new lower pressure. And once it finally establishes that new balance, the liquid inevitably turns completely flat.
And this perfectly builds our understanding of the different types of systems chemists observe out in the wild. First, we have homogeneous equilibrium. This is where all the reactants and products exist in the exact same phase. So like a reaction that's entirely between gases or entirely mixed within an aqueous solution. On the flip side, a heterogeneous equilibrium features a system with more than one phase. Our soda bottle, which has a liquid phase and a gas phase existing right there together, is a flawless example of a heterogeneous system. The really amazing part is that the math, that exact same balancing act we just learned, applies beautifully to both of them.
To wrap up today's explainer, I really want to leave you with this remarkable quote from the source material because it highlights exactly why all of this actually matters to you and me. It says, "Equilibria involving O2 molecules in the protein hemoglobin play a crucial role in the transport and delivery of O2 from our lungs to our muscles." I want you to really think about that for a second. With literally every single breath you take, oxygen enters your lungs and forms a dynamic equilibrium with the hemoglobin in your blood. Then when that blood reaches your oxygen-starved muscles, the physical conditions change, the equilibrium suddenly shifts, and the oxygen is released right exactly where your body needs it. This unseen chaos, this continuous, invisible balancing act of chemical equilibrium, it isn't just some boring textbook concept. It is literally the very mechanism keeping you alive at this exact moment. Doesn't that kind of make you wonder what other invisible balancing acts are happening inside you right now?